Again, welcome to this NPTEL course on Advanced Prestress Concrete Design. We are in the module on Flexural Analysis and Design. Now we are moving to the part 5 of this module 4. In this, we are going to talk about flexural design of statically determinate beams and type 1 and type 2, and also we will spend some time on the detailing requirements. That means how to put the steel, what are the minimum requirements for steel, both pre-stressing steel as well as non-pre-stressing steel, and so on. Okay, the expected learning outcomes are going to be understanding the flexural design of type 1 and type 2 members and detailing requirements for pre-stress members. These are the main expected learning outcomes. Okay, in flexure design, we categorize them into two steps. The first step is basically preliminary design. So, when you talk about design, again you have to keep in mind that design also what we are actually doing is we are doing actually analysis, okay, and design is an iterative process, okay. So, that means we assume certain details and then check for the capacity. If those details are not good enough, then we keep changing them until we meet our requirements. That's why design is an iterative process and you need to do a lot of iterations to come up with an optimized design. So, what is the meaning of a preliminary design in case of a pre-stressed concrete section? So, here if you see in preliminary design, broadly we should have an idea of what type of section that we need to choose. For example, buildings typically we go for a rectangular cross section, or if you are doing sometimes precast systems with more number of volume of same type of element, then I can go for I section or T section also. But typically in buildings we will have rectangular sections which are common. But if it is a bridge, let us say I am doing it for 15 kilometers of nearly same spans, then typically you will have standardized sections and then I can optimize a mold for creating these sections. In preliminary design, again we should broadly see what type of section that we need to choose, and then we should select the material properties, FCK. Typically that is also kind of fixed depending upon what kind of design that you do. FPK is typically it is 1860 megapascal we have seen, and FCK either 30, 40, 50 or 60 depending upon the nature of the project that what you are working on. Then we estimate the values of lever arm and the effective pre-stress. So, this is a critical thing. So, we kind of see for a particular with some assumptions, because the span will be known to us, then we assume some sectional details based on the preliminary thumb rules, and then we see how much is the lever arm that is required, and then from there we calculate your effective pre-stress. We kind of know what is the amount of pre-stress that is required, and here also based on this we assume the dimensions of the section, that means the depth and width of the element. This is preliminary design. At the end of preliminary design, you kind of come up with the type of cross section and their dimensions and the amount of pre-stress that is required. That is it. But you do not know where that pre-stressing force and the layout of the pre-stressing cape, you do not know at this stage, which is at the preliminary design. And that is what we say. In the final design, we exactly calculate what is the eccentricity of the pre-stress and the profile of the cable. That is the next level of detailing, right. Then based on the assumed eccentricity or calculated eccentricity and the profile, we are going to calculate the effective pre-stress and the exact area of pre-stressing steel, right. So, and then finally we check for the stresses, compressive stresses at transfer and service, okay. Again, if it is a type 1 member, you have to check for type 2 tension stresses also, okay. So, we check for that as well. So, these are the steps. In preliminary design, we broadly come up with the dimensions of the cross section and the amount of pre-stressing or the area of pre-stressing steel, right. In the next step, we should also calculate the exactly the eccentricity of the pre-stressing cable. So, and then finally we check whether the assumed section is satisfying all the stress limits. Now, what are the criteria for selection of your sections? So, if you see, the type of section is selected again as I discussed based on the use of the structure, architectural requirements, casting and fabrication options that are available. For example, let us say I want to create a box section of a very unusual dimensions, but if I have to make large number of volumes of such element, then I can fabricate a mold, right. So, if the number of elements are going to be less, then I should not use different cross sections. Then the cost of the formwork will become high, right. So, it also depends upon construction and the type of structure that you are using and the architectural requirements. Sometimes the sectional shapes have to be decided. Okay. So, in general, if you look at it, the section should have large depth below CG of the concrete section. That means what? Large depth below the CGC so as to have large eccentricity, because we wanted to have higher MP, which is nothing but P into eccentricity E. E can be high only if your depth below CGC is higher, right. So, only this is possible if the depth below the CGC is higher, right. So, that is the reason the section should have large depth below CGC. Then the amount of pre-stressing force can be reduced. In turn, then I need to have, then I will end up with a less area of pre-stressing steel AP. Okay. And there should be adequate concrete at the top and bottom to satisfy the allowable stresses. That means, you put more area at the largest distance from the neutral axis. For flexure, typically for flexure, I need to put more area where the stresses are going to be high. In flexure, from the strain gradient, you know that the stresses are going to be higher for a larger distance from the away from the neutral axis. That is the reason we need to have adequate concrete at the top and bottom to satisfy the allowable stresses. And usually what will happen, if you see, the end section will be solid to increase the shear capacity and prevent anchorage zone. So, what is the meaning of that? Let us say you have this kind of an I section that you have at mid span, right. Okay. This kind of I section, this is at mid span, right. Now, this can be converted to a rectangular section. That means I will make entire thing as a rectangle at support to satisfy shear, as well as because lot of pre-stress will be anchored at the end. So, you will have sometimes you have to splay the tendon so that the stresses are going to be less. So, we make this I section into an equivalent or like this kind of a rectangle I will make only at the edges close to the support region, right. Now, let us see, we have studied this in the first part of the module. You can see that these are the recommended span to depth ratios. If you see for one way solid slabs, if I am doing pre-stressing, this is again whether if it is a continuous span or a simple span. This is basically simple span is this, right. Continuous span is this, you have multiple supports, right. So, if you have a member in continuous span, one way slabs for floor, the allowable span to depth ratio is 45, and for roof it can be lower, because typically the live load requirement for the roof will be lesser. So, that is the reason typically roof will have higher L by D ratios than the floor slabs, which will be usually be subjected to higher live loads, right. So, similarly, if you look at for two-way waffle slab, if it is pre-stressed for a roof element, I can have 40 allowable L by D ratios, and then for floor it is 35. Beams, we have seen that 35 and 30, and if it is a simple span, again that value slightly comes down by 10% or so, right. So, for beams, if you see here, the roof element for a continuous system I can go slightly higher because a lot of redistribution is possible, higher L by D ratio is allowed, but if it is a simple thing it goes from 35 to 30. So, there is a reduction in L by D ratio for a simple span because redistribution of stresses are not possible, right. One way joist again you can see 42 for continuous span in roof and then simple spans 38 for roof, and floor will have slightly lower value which is 35. In general, if you look at it for RC without any pre-stress, span to depth ratio will be typically 20 to 30% lesser than the values that are suggested in this table. Okay. So, that is a big advantage with pre-stress. This is only a guidance. Of course, if you come up with more reinforcement or unique design, this value can be even higher, 20 to 30, maybe 40, 50% also. But this is a generic thing that for reinforced concrete, typically if you see span to depth ratios will be obviously 20 to 30% lesser than pre-stressed of equivalent design. Now, what are the steps involved in preliminary design? As we have said, assume FCK and FPK. For example, let us say I assume 40 megapascal of concrete and FPK is 1860 megapascal. So, this I have assumed. Then what I do? I have to assume depending upon the span for the given L by D ratios, right. For a beam, let us say that I take about 30 or so. Then if I know the span, I can find out the depth. Then the depth also can be calculated from this empirical formula, which is 0.03 square root of m to 0.04 square root of m, where h is in millimeters and m is in kilonewton meter, and typically m is excluding self weight, right. So, once we know the depth, now how do we get your m, right. So, this is a function, this is a we assume m. So, you know the kind of live load that are coming, what are the loads, so you know the span. So, you kind of get from assumed structural analysis by assuming some member dimensions, you can come up with m and then recheck what should be your h that it should be there, right. Now, the total moment, then the next step is to calculate the total moment including self weight, where MT is defined as the total moment including the self weight, right. Then once we do that, of course, we have not still assumed the entire sectional shape. So, in that we can say that 10 to 20% of the total moment is carried by self weight moment, typically denoted as MSW, right. And this is an assumption, again we have to check. That is why I said design is an iterative process. You assume certain things, come up with a preliminary design and then you optimize your design, right. Then we select the type of the section. For example, if you take rectangular section, either you can take B is equal to h by 2 or B is equal to, you can say 0.3 times h, or B is equal to 0.4 h, depending upon your allowable things. Typically for flexure, you try to keep breadth low as possible, but it should, and unless the torsion is governing, the breadth also will come into picture, but for flexure and shear, it is the depth that will play a major role. So, you want to maximize the depth with the given area. So, you try to, from architectural requirement, whatever the minimum breadth that is possible, that we try to keep it. Typically, the range is 0.3, 0.4 or 0.5 h. Now, you see here, now that we have assumed this, and then from here we have calculated what should be the depth that is required and so on. Now, we can go ahead and calculate, as we have seen in your analysis. If you remember, this is your CGC and this is the level of your, right. Let us say this is your, so what we are trying to see here is, again, when no load is acting, let us see, C is here and this is your T, right. Now, this is when no loads are there. When loads are acting, with loads, what we have seen is this C, if you look at it, right? C would have under service loads, let's say C is here. This is the location. So how much distance that the C has moved, this is what we say as Ez, which is nothing but your eccentricity plus EC, right? So Ez is always equal to E plus EC, right? So we don't know this, right? So we are saying that we are going to assume some lever arm, Ez equal to 0.65 H, right? That's what we are saying, approximately if sulfate is large. When do you say sulfate is large? Let's say that with assumed dimensions you calculate your sulfate. Again, you know the span, you know assumed dimensions. From here I can calculate what is the sulfate moment. Okay. So if the sulfate moment is working out to be more than 30% of your total moment, then we say that lever arm you take it as 6.65%. Because why? When sulfate itself is acting, C would have slightly moved up. Then when live load is acting, that will even move further up, right? So the lever arm will be higher if your sulfate is much higher. If sulfate is lesser, then the lever arm can be assumed as 0.5 H, because right, see, sulfate is lower, then it would have moved slightly only, then further movement. So depending upon the amount of your sulfate moment, now my lever arm will be higher or lower. So that's why we are saying if sulfate is higher, the lever arm to be taken to be higher, which is again an assumption. We have to, this is from preliminary design. Once the lever arm is known, now that you know the total moment, now we can go ahead and calculate the effective prestress required. Now effective prestress, we know that it is equal to C, which is equal to PE, which is equal to total moment divided by the lever arm. Lever arm you calculate it, right? If sulfate is smaller, then we say we take only imposed load divided by lever arm. That will be equal to your compression force again. So in this way, we complete the preliminary design, right? So you can assume a depth from an empirical formula or your L by D ratios, and then choose your width, and then once breadth and depth is fixed, you can go ahead and calculate, because span is given to you, you know the external loads, you can calculate your total moment, then you can assume lever arm and you can calculate your effective prestress required. Now we have to, at the end of preliminary design, again whatever the dimension that we have chosen, the average compressive stress in concrete should not be too high compared to 50% of the allowable stresses. That means I select PE by area in such a way that this should be less than half of FCC allowable. That's what we are trying to say. This is for preliminary design. Okay, so this is what we are trying to do. And if it is so, then if it is not satisfying, because at this stage we don't know the eccentricity, so there will be a pre-stressing moment and load component also will come. So from preliminary design, you choose area in such a way that PE by A should be less than 50% of your allowable stress in compression. Now once PE is known, this is known, then I can take effective prestress as 0.7 times FPK. If we go back, FPI we take it to be 0.75 times FPK. Now here I am saying that some losses, 5% losses would have happened. So let's say that I take 7.7 times FPK and then calculate my area of pre-stressing steel as effective pre-stressing force divided by the effective pre-stressing stress. Then we have to check the provided area has to be greater than your, or the provided cross section should satisfy the allowable stress limits, with the fact that PE by A should be less than 0.5 of FCC allowable. Now let us see what are the steps. Now this is at the end of preliminary design. Preliminary design, we know what is the depth and what is the width of the cross section, and what is the shape of the cross section also, and what is the effective pre-stressing force and area of pre-stressing also we know. But what we don't know is what is the maximum eccentricity I can keep this pre-stressing force. That I don't know yet. That is what we are trying to get it in final design. Now you see what are the steps. The first step is to calculate eccentricity to locate the CGS. That is nothing but your eccentricity calculation only, right? So again we have some procedures for small moments due to self-weight. That means self-weight moment, if it is less than 30% of a total moment, then as we know, when the loads are increasing, compression force moves upward from the location of tension force. Therefore, a transfer under the weight C should lie within Kern zone to avoid tension stress at the top. So C should be within the Kern zone for a type 1 member, right? So this is for type 1. For type 1 member, this is what it is. So based on the self-weight transfer, now you see here, this is when no weight, C is at the location of T. Now when self-weight is acting, now what will happen? The C will move from, for example, let's say this is your CGC and this is your CGS. That means my eccentricity is this, right? So now if you see here, the C has moved up by some magnitude, okay, and we are calculating that magnitude, okay. Now you see that, but this is at the lower Kern point because it's a type 1 section, the type 1, okay. So that means for type 1 a transfer, if you look at it, my stress at the top should be equal to 0. Stress at the top should be equal to 0. So the C by A will be equal to P naught by A. Here 0, here it is some stress because of this, and so the average stress is going to be P naught by A. Now the shift, how much C has shifted up is proportional to your self-weight moment, right? So that is the lever arm. So this distance now shift, let's say that as delta Z, right? Now what is delta Z? If you look at it, delta Z is going to be equal to E minus KB, right? Now that delta Z is the moment of C. That means what moment it has created? P naught into delta Z should be equal to the self-weight moment, because the self-weight moment has pushed P naught or C by a distance of delta Z, right? So I can substitute for delta Z as self-weight moment by P naught, which is equal to delta Z, right? Okay. Now if we know this, we can calculate for this what should be the eccentricity that it is possible based on the self-weight moment. Because KB is known to you, self-weight if it is known, then you can substitute and you can find your eccentricity value, right, for the transfer condition. So you get one eccentricity to satisfy the stress limit for transfer condition. This is the way you get your. So E as per this equation should be equal to MSW by P naught plus KB. This is the eccentricity that we get. Now if you go back, what should be now P naught? So the C or T is equal to P naught. Now the value of P naught, depending upon whether it is pre-tension or post-tension. For pre-tension, as you know that elastic shortening will be there, and so Pi or P naught can be taken as Pi multiplied by 0.9. For post-tension, there is no elastic shortening. Typically, if the cables are tensioned simultaneously, so typically we take P naught equal to Pi for a post-tension system. Now, what is the value of Pi can be, now we can estimate it from your initial pre-stressing as AP into 0.8 FPK. The permissible stress in the pre-stress steel is 0.8 FPK. Now here I have taken 80% of characteristics. If you don't want, you can also take Pi to be AP into 0.75 times FPK. So different codes give you different values, but typically 75% is good enough. Okay. So I have taken permissible stress for initial is 80% of FPK, and FPK is the characteristic, but you can take 75 also. There is no hard and fast truth, but you cannot typically exceed more than 80% of your characteristic strength. Okay. So, now we got your eccentricity and the pre-stressing force Pi, right. Now, we go back and check what is the recompute the effective pre-stress and the area of pre-stressing. This is the final design. Now, the previous step, now how do we do that? Now, we go to the service condition based on the moment and demand that are at service conditions. From the transfer condition, we use those values, updated values, and check what is happening, right. Now, if you look at again for service conditions, this is the moment that it is acting. This is the total moment, right. So, typically we take it from 1 dead load plus right, at service 1 live load, right. So, this is service, not the ultimate, right, service condition, the moment is acting. Now, the C would have gone all the way to the top, and now it is at a distance of kT, right. Again, T and C at the same location, C will keep moving upward. Now, at service, K will be at the location of your upper current point. Now, how much distance it has moved? So, this is going to be this, which is nothing but E plus kT, right. So, that is the total distance it has moved, or the lever arm is going to be Z going to equal to E plus kT, right. Okay, so this maybe you can write that as Yt and Yb. Typically, we take Y as a nomenclature, so you can take Yt and Yb. And here also the stress in the concrete, if you look at it, the average stress is going to be Pe by A, or C by A is nothing but Pe by A. Now, the shift of C, how much it has shifted? Again, it is a function of total applied moment. Now, you can see Mt has to be resisted by C into Z, which is nothing but E plus kT. So, that is what we are saying. Now, Pe will be equal to Mt divided by E plus kT, effective pre-stress force, because Pe is going to be equal to C, right. So, compression force should be equal to your effective pre-stressing force. Now, if you consider effective pre-stress as 7.7 times FPK, the area of the pre-stressing steel is recomputed as AP is equal to PE by FPE. Again, I am telling you have to check for the condition at transfer, then you also check for condition at service, and then you keep updating your value and you find the final value. So, this is based on the service condition, AP will be P by. Now, again in service condition, FPE is taken as 0.7 times FPK. That means, if you see FPI, we have taken 0.8 FPK. That means how much it has lost? About 10% of FPK is lost due to loss of pre-stress, right. So, because of this, now I am going to get there is a change in AP and P naught based on the loads at service. Okay. So, now based on the service conditions, the previous calculations in AP and P naught have to be updated based on the latest service conditions, moment calculations at service condition, right. So, now let us see how do we recompute the eccentricity. Now, what do we do? So, again the value of P naught is updated. Now, that effective P is updated and the eccentricity is recomputed with the updated value of P naught. If the variation of the eccentricity from previous value is large, then one more cycle of computation is to be done. So, this is an iterative process. So, that when we go through an example, it will become very clear to you, because we are doing calculations at multiple stages, right. Now, let us look at. So, finally, now that let us say that the eccentricity from the previous iteration and this iteration is the same. Now, we can say that we have kind of come up with amount of pre-stressing and the location of your pre-stressing force. Now, for this we need to check the compressive stresses in the concrete. Now, the maximum compressive stress in the concrete should be limited to the allowable values. So, what are the allowable values? Code IS 1343, it gives you this limits. Okay. This is for pre-tension, right, and this is for post-tension. So, these are the stresses. For M40 it is 0.51 FCK, for M60 it is 0.44 FCK, and so on, right. These are the values. So, we have to satisfy this. So, depending upon the grade of concrete, for example, if I have to do, let us say for M50, then I have to do the interpolation. So, this for M50. Okay. So, we have to do the interpolation. Now, this is for service. This is a transfer. Again, at service, there are two zones that are given, zone 1 and zone 2. Zone 1, you can go for a slightly higher stress, because those are all zones where your stress can be slightly allowed to exceed. These are all the permanent stress zones, and these are your transient zones where for some period of time due to construction loads and so on, you can allow to have slightly a higher stresses. Okay. So, this is for the stress limits. Now, let us look at it. How do we get that? Now, for type 1 member, we know that the stress at the bottom can be calculated as P naught by A times H by YT, right. So, this is the way that we calculate. Now, if you assume that the magnitude of the stress at the bottom has to be less than FCC allowable, then the area from this can be calculated as should be greater than P naught into H by FCC allowable times YT. If A is not adequate, then the section has to be redesigned. That is what we do. Now, again, transfer, if you look at it here, right. So, at transfer, compression will be at bottom. At service, compression will be there at top, right. So, the stress at the top can be calculated from average stress again PE by. The only thing is at service the pre-stressing will become PE, and same, because we see here this is what we show, and we allow anyway 0 here. Okay. So, this is at the bottom 0 here, and this is some stress FCC. So, we are trying to calculate this. What would be if this is PE by A, right, and for a distance of H, how much? So, this distance will be H by YB, what would be the stress? So, this in a way this is PE by A, right. So, I am doing the interpolation. This is kind of multiplication factor to get what is the stress at the top, which is FT. That is what we are doing here, right. So, for H by YB distance will be this from similar triangle. Basically, from similar triangle, we are trying to get what is the stress at the top. Similarly, for this one also, it is this. This is P naught by A, and we are trying to calculate the stress at the bottom, which is your P naught for A multiplied by H by YT. Okay. Now, this is the distance YT, and this is the distance YB. So, using that we can calculate. Again, if the area is not adequate, then the section has to be redesigned. Okay. I have to check for both allowable compression at transfer as well as at service.